Behind the scenes, today's video on glycolysis and the tricarboxylic acid cycle. Super early in the morning, the birds are losing their minds, and I'm about to show you exactly what glycolysis is and how your body burns sugar for energy and how your body makes a ton of energy just from burning a little bit of sugar. So you eat a super sugary meal, maybe you ate bananas, a fruit smoothie, or maybe you went a little crazy and had like full-on chocolate cake. Well, now there's sugar in your blood, so you have blood glucose or a blood glucose spike. What your body's gonna do now, or what your cells are gonna do, is they're gonna start taking that sugar, that glucose out of the blood into the cell and begin metabolizing it. The end goal is to oxidize that glucose molecule all the way through glycolysis, through the tricarboxylic acid cycle, and through the electron transport chain to get a ton of ATP. ATP is actually usable energy to your body. To actually get to that end step of oxidizing glucose in the respiratory chain or the electron transport chain, you need to do glycolysis first. So glycolysis is part one of sugar burning, and it is absolutely essential. It is your body's most quickest, rapidest, speediest way to get energy from sugar. And there are the Mexican birds getting excited about glycolysis with us. So, okay, yeah. Glycolysis, sugar burning part one, anaerobic. It happens without oxygen. So glycolysis is a really good way for your body to rapidly metabolize glucose in conditions of low oxygen or like high performance activity. So sprinting, like playing hockey, or explosive high intensity workouts, your muscles are probably going to be doing a lot of glycolysis because it's just such a fast way to burn sugar and make energy. If there's low oxygen, you can't oxidize glucose, so you're kind of stuck with doing glycolysis for energy only. What else? Oh yeah, glycolysis. If you're doing a lot of glycolytic activity, that's when your muscles are gonna really feel the burn, because when you are doing more glycolytic activity, more lactic acid is being produced, and that lactic acid is what causes the burning sensation in your muscles. Now, part two, inputs and outputs of glycolysis. Here's our little glycolysis bubble. This is gonna set you up with everything you need to know to actually understand the biochemical pathway of glycolysis. So what is going in? Well, first of all, we said glycolysis is burning sugar. So we know a glucose is going in, and glucose has 6 carbons. This can't happen on its own. Glycolysis needs enzymes, cofactors, ADP, phosphates, and ATP to actually happen. So we also have going in 2 NAD+. Glycolysis also produces 2 ATP, 2 net ATP. It produces 4 ATP and it burns 2 ATP. So it produces 2 ATP net. So to make an ATP, we need 2 ADP and 2 P going in. The 2P is 2 phosphorus. So our inputs to glycolysis, 2 NAD+, 1 glucose, a 6 carbon molecule, 1, what the frick did I write? 2 ADP and 2 phosphates. Our outputs of glycolysis, this is exciting. What we get out is we get 2 NADH. So this is NADH reduced, and it is a high energy electron transport molecule. Then we also make, see, 2 ADP plus 2 phosphates makes 2 ATP, because ADP is adenosine diphosphate, ATP is adenosine triphosphate. So 2 plus 1 equals 3, ADP plus P equals ATP. And then lastly, this glucose, the whole purpose of glycolysis is to get this glucose into a form that can enter the tricarboxylic acid cycle, and then we can extract even more electrons from it and send those electrons to the electron transport chain. So when we are sending glucose down into glycolysis, when sugar is going into glycolysis, what we get out is 2 pyruvates. This is so messy, but here we see 2 pyruvates, and pay attention to this. We have 1 glucose going in. Glucose has 6 carbons. We have 2 pyruvates coming out, and pyruvate is 3 carbons. This is super epic because just this anaerobic respiration, anaerobic metabolism of glucose has given us something we can further process and extract more electrons out of. It's given us a teensy bit of ATP, and we've gotten some high energy electrons from this metabolic pathway as well. Part 3, the actual metabolic pathway of glycolysis. Start with sugar, process it all the way down here by all these enzymes. Enzymes are made out of protein, by the way, and we end up with pyruvate, 2 NADH, and 2 ATP. Now your body can send that pyruvate down pyruvate processing and make a ton of ATP. This is a really good thing. Okay, so how does this even start? It starts with glucose. Glucose enters the cytoplasm. The first enzyme that acts on glucose is hexokinase. Hexokinase, it's a kinase of hexoses. Hexoses are 6 carbon sugars, and we already know that kinases are enzymes that phosphorylate things. So what hexokinase is doing is it is taking an ATP, ripping off that phosphate, and sticking it onto glucose. That gives us G6P, glucose 6-phosphate. The whole purpose of this step is because glucose can enter the cell through a GLUT4 receptor. G6P cannot travel through the GLUT4 receptor. That receptor is specialized for insulin. So this phosphate, with its PO43-, that negative charge, having now this negative charge on glucose, literally it can't escape the cell. So now glucose is trapped in the cell and it is committed to glycolysis. So this is your first commitment step because this is trapped in the cell, can't go anywhere. Its only choice is to go through glycolysis. Next enzyme, Phosphohexoisomerase. This turns G6P into F6P. So we go from glucose 6-phosphate to fructose 6-phosphate. And this enzyme is Phosphohexoisomerase. So it isomerizes hexoses with phosphate groups on them. This is a hexose and it has a phosphate group. It's glucose here. Now it's fructose. It's been isomerized. Phosphofructokinase 1. This is your second commitment step in glycolysis. This gets us from F6P into F16BP. It uses one ATP molecule, rips off the P, and it sticks it onto F6P. Now instead of F6P with a phosphate in the 6th carbon, we have F16BP. Fructo 1,6-bisphosphate. So there is a phosphate in the 1st carbon position and in the 6th carbon position. So it's literally like a little sugar molecule like this with a phosphate here and a phosphate here. The 1 carbon and the 6th carbon, both are phosphorylated. Next enzyme is, this part is confusing for me sometimes, aldolase. Aldolase chops F16BP into 2. So aldolase kind of does this. That leaves us with DHAP and GA3P. This DHAP is like a teensy bit useless. This GA3P is super awesome and we can send it all the way down glycolysis. What we need to do to this DHAP is turn it into GA3P. We are going to use the enzyme triose phosphate isomerase because this is a triose, a 3-carbon sugar. It's got a phosphate attached and we need to isomerize it, reorganize its carbon skeleton. Now we have 2 GA3P and we can continue down glycolysis. Now we're going to use the enzyme GA3PDH glyceraldehyde 3-phosphate dehydrogenase to oxidize and phosphorylate GA3P into 1,3-BPG, 1,3-bisphosphoglycerate. So NAD plus is coming into this reaction and phosphate is coming into this reaction. This spits out NADH, so NADH reduced. It is a high energy electron carrier represented by that H. And then 1,3-BPG, so this is this molecule, except it's now phosphorylated and it's lost some hydrogens. Phosphoglycerate kinase. Recall that anything that is a kinase is an enzyme that's dealing with phosphorylation. Phosphoglycerate kinase brings an ADP into this reaction. It converts 1,3-BPG into 3PG, 3-phosphoglycerate. And when it takes that phosphate off of the first carbon position, it sticks it onto ADP and it spits out an ATP. So we go from 1,3-BPG, phosphates on the first carbon on the third carbon, to just 3PG, only a phosphate on the third carbon. Now we have 3-phosphoglycerate. We use the enzyme phosphoglycerate mutase to mutate 3PG into 2PG. Literally, this is just like a little rearrangement. It moves the phosphate from the third carbon to the second carbon. So we go 3PG to 2PG. Next reaction, 2PG, and we use the enzyme enolase. Enolase turns 2PG into phosphoenolpyruvate, PEP, and it spits out a water molecule. So this reaction is a little bit exciting because it literally makes water. You go from 2PG to PEP and you make a water molecule. Now we're at PEP, phosphoenolpyruvate. This is when we actually finally finish glycolysis and make pyruvate. Pyruvate kinase, it's a phosphorylating enzyme because it's a kinase. We have ADP coming into this reaction and ATP going out. We have phosphoenolpyruvate coming into this reaction and normal pyruvate coming out. What pyruvate kinase does is it takes this phosphate and it sticks it on to ADP. So now we spit out ATP and a pyruvate. Finally, glycolysis is finished and we have our end goal molecule of pyruvate. Pyruvate is now going to be further processed. If oxygen is present, pyruvate is going to be oxidized and processed into acetyl CoA. Acetyl CoA is going to enter the tricarboxylic acid cycle. It's going to combine with oxaloacetate to make citrate. That cycle is going to spin and we're going to make a bunch of NADH and FADH2. We're going to make some carbon dioxide gas and breathe that out. And then those NADHs and FADH2s are going to dump electrons into the electron transport chain inside of your mitochondria, and we're going to make so much freaking ATP. If there is no oxygen, then this pyruvate is just going to stay in your cytosol and it's going to be fermented into lactic acid, and this whole glycolysis cycle is just going to go on over and over and over again, and we're not going to be making that much energy. So there you go. That is exactly what glycolysis is. That's the biochemical pathway of glycolysis, the inputs and the outputs, and this is setting you up with everything you need to know such that you can better understand the tricarboxylic acid cycle and the electron transport chain, so how your body actually makes high amounts of ATP. Now, glycolysis obviously is a ridiculously critically important metabolic pathway to your body, to your cells, literally to have energy and be alive. Like everything kind of depends upon glycolysis. This is where energy is coming from. This is part one of actually making useful energy to your body. So naturally, glycolysis needs to be regulated. So my next video is going to be on how insulin and glucagon, these two hormones, regulate and control glycolysis so it happens when it needs to happen, where it needs to happen, and in the right volumes. If you got any value out of this video, if you enjoyed it, if you learned something super cool, epic, and exciting, like, comment, and subscribe. It helps me put more time, energy, and resources into these videos and make them higher quality and more impactful for you. So I'll see you in part 2 and have an awesome, lovely day. Bye-bye, everybody.